Okay, so welcome to the NPTEL TA session for Introduction to Robotics week 4. I am Suraj Borate. I am PMRF PhD student from IIT Gandhinagar. And the purpose of this session is to help you with your uh, ongoing assignments, weekly assignments, and solve some questions that are pertaining to the old assignments that have been covered previously, so that you can get some hints on how you can solve the current assignments. Okay, so let's begin with our first question for the week 4. So this week we will be covering Jacobian and inverse kinematics related questions. I hope you have gone through the lecture materials, and if you have any doubts you can ask. Okay. So is the screen visible? Are you able to see the slides?
Yes, sir. Your screen is
Yeah.
visible.
Okay. So let's go for the first question. So choose the conditions which are necessary to be satisfied for a manipulator to be solvable. Okay, so when they are saying manipulator to be solvable, it just means that inverse kinematics to be solvable, or from the end effector positions, can we get the joint angles or not? That is the meaning of the question. Okay, so if you see the first option, tool orientation is such that none of the joint limitations are violated. Of course, if joint limitations are violated, then we don't want that to happen. We cannot solve that. The degree of freedom must be less than or equal to 6 to have an any arbitrary orientation of the tool. Okay, so what does that mean? Suppose if it is more than or greater than 6, then what will happen? Then
So
there will,
if it is more than six, then it will be a redundant system, I think.
yeah, but what about the solvability? How it is going to affect the solvability?
Okay. I'm not quite sure of the answer, but a redundant system has limited solvability. So I was not being able to recall how it affects.
Yeah, yeah. So what happens is if there are more joint variables, right? So there are more variables and less number of equations. Okay, we only know the end effector position and end effector orientation. So we know six data points we have: three position coordinates x, y, z, and three orientation coordinates. We will pitch here. So from six we have to find more than six. So six data points means six equations we have, right? And from
Yes,
six
yes.
equation we have to find 7 8 unknowns. Then that is not possible. Okay, so that is the intuition. So this is also correct. It should be less than, not greater than 6. Okay, the tool point should be within the workspace. Of course, it should be within the workspace. If there is it is outside the workspace, there is no solution. If the end effector position is outside the workspace, then no combination of link angle or joint variables can reach that point. So there is no solution. The tool point can be outside. No, it cannot be outside, because just now we discussed the freedom should must be greater than. No, it should be less than or less than or equal to 6, because if it is greater than, then we have, as we have just discussed, number of equations will become greater than number of, sorry, will become, okay, I need to erase this. Okay, so number of equation will become less than number of variables, because if degree of freedom is greater than 6. Okay, so I also gave the logic. People who are joining late might miss this, so I will just repeat for the those who have joined just now. So in this particular question, the this particular point is very important, the second point. Okay, so the degree of freedom must be less than or equal to 6 to have any arbitrary orientation of the tool. Why? Because we have three position variables px, py, pz, and roll, pitch, and yaw. Okay, now these six variables of end effector we know that we have the data, and from that we need to find the joint angles theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, right? But if suppose we have to find more, if it is a redundant manipulator and there are more degrees of freedom, then we cannot find more variables from six equations, right? So that is why we need degrees of freedom to be less than or equal to 6. Okay. Okay. So the remaining 2 points were simple, so I will not repeat them. Okay. So which of the following is the sufficiency condition for the existence of closed loop solution? So actually this is a printing mistake. This is called as closed form solution. Okay, what is the meaning of closed form solution and to what equation it is? So it is the we are talking about. So let me give the context. Closed form solution of inverse kinematics problem. Okay, complete question should be like this. Okay, so what is the sufficiency condition? So the answer here is that, okay, so first of all, what is the meaning of closed form solution? So closed form means that if we can get a formula. Okay, we can get a formula. Like for Pythagoras theorem, we have a formula, right? Like for Ohm's law, we have formula. Newton's law, we have formula. So we should get a formula as what is the relation between theta 1, theta 2 as a function of let's say x, y, z, and roll pitch yaw of the end effector. Okay. Net. Okay, I got disconnected. Can you hear me now?
Yes, yes. We thought you were on mute, so I was
No,
probably
no,
asking.
I got disconnected. Some internet issues are there. Okay, I will
Okay.
share the screen. Okay, okay. So let me just check. Okay, everything is fine. So yeah, so I was talking about the closed form solution. Closed form solution means there exists a formula where we have what we want to find can be represented as a function of let's say x, y, z, and roll pitch over here. Okay, Anirudh, you can just speak out directly without raising the hand. Yeah.
We are unable to see your presentation, sir. We can just see the infinity screen.
Oh, okay, okay. Let me check. Let me check.
Right.
Thanks. Entire screen. Now you can see.
Yeah, yeah, it is visible now, sir. Thank you.
Okay. Uh, so yeah, so the you can write it as a function of the end effector position and end effector orientation, the angles. Okay, so that is what is called as closed form solution. Means there should be a formula that exists. So in inverse kinematics, it's forward kinematics. There will always be a formula because you find the homogeneous matrix for each link. You multiply all the homogeneous matrices, and then at the end you know our favorite column, right? The fourth column and the three rows. You find out the values from that. But for inverse kinematics, it is not easy to find the angles. So what you do is the steps involved in inverse kinematics is this: you find that manipulator matrix, right? You find this rows, and what you will get that these three values will be function of all your joint angles and all. Okay, usually function of joint angles. This will be x will be also function of some joint angles, and this will also be a function of some joint angles and all. But you will get three equations, right? But then it is very difficult to solve these three equations. uh, Sometimes it is solvable, sometimes it is not solvable. So what is the condition for it to be solvable? That is the meaning of the question. And the conditions are this: the three adjacent joint axes should be intersecting, okay, or the three adjacent joint axes should be parallel. Either they are intersecting or they are parallel. Okay, they should not be perpendicular to each other. So that is the, yes. Any question?
Ye- Yeah, yes, sir. I just want to confirm if my assumption is correct.
Okay.
So, with this statement, are we referring to that if there is translation within each joint of the manipulator body, then we can consider that the inverse kinematics is solvable?
Just translation, yes, that is also possible. Yeah, but that is one
Because
case. There can be other cases where it is solvable. It is one case. So, for example, what you are saying is 2R manipulator. So there is this axis and there is this axis which are perpendicular
yes,
to the plane. Or they both are
yes,
parallel, so it is solvable. Yes, it is solvable. And there is one translation between them. Okay, but it is not just translation. There is a angle theta 1 also here, theta 2, but the axes are parallel. Okay, yeah, that is
right,
true. Yeah, but yeah, the logic behind this or the proof behind this, I am also not available, and even the lecture sir has not given. So let's not
right,
go into that. And if you find anything, you share with me also. I was not able to find any proof for these two statements. Okay. So three
sure, sir.
adjacent joint axes parallel to one another, or three adjacent joint axes intersecting. So the importance of this is that when you are developing your manipulator robotic arm, you when you are choosing your joints, how and links, you if you pay attention to these two details, then it will be good because your arm will have what we say possibility of calculating inverse kinematics. Otherwise, it is not that you cannot calculate. There are something called as iterative method of iterative methods for calculating inverse kinematic. So here you will not get a solution. Sorry, you will not get a closed form solution or a formula, but you will get a procedure by which a numerical procedure by which you can solve numerically the inverse kinematics. If you search for iterative method for inverse kinematics, you will get, but that is out of the scope of the course. And but still, I think you should go and learn this. It is a good thing to know. Okay, so let's go on to the next question. Determine the Jacobian matrix for a force 4-axis Cara manipulator that is shown in the figure. Given the positions are this. Okay, so Jacobian matrix, the word, this is the word that is coming for the first time in our sessions. So what is the Jacobian matrix? What is the significance of the Jacobian matrix?
It's actually the partial derivatives of each of the values of px, y, and z with respect to
Yeah,
t.
yes. So the Jacobian matrix, basically it is important because it relates the end effector velocities and angular velocities to the joint velocity and angular velocity. Okay. So this particular matrix that relates these two is called Jacobian matrix. As far as the robotics community is concerned, we identify that like that. Or it also relates the end effector torque to the, sorry, it relates the joint torque. So it is this is a vector of all the torques at all the joints, like we have theta 1 theta 2, right? So tau 1 tau 2, like that, how many links you have, that is related to the force applied at the end effector tip. So how much force the end effector is applying. So suppose you have an end effector, and it is gripping some object, so and it is applying some force, right? Not within the grip, but let's, instead of gripper, let's take another example. It's just you have a end effector which is holding a chalk. Now the chalk, with that chalk you have to write on the wall, so you have to apply some force to write. So how much that force is, let's say fx, fy and fz is the force that end effector is applying on the environment. To generate that much force, what should be the joint torques that should be applied? So how much each motor, or the each at each joint, how much torque should be applied? Okay, so that is like tau 1 tau 2 tau 3. So this is one relation related to Jacobians, and this is another. Okay, so how to compute Jacobian, that we will see. So this is the importance of Jacobian for robotics. Okay, so in general, a Jacobian matrix, okay, relates two spaces, right? So one is joint space and Cartesian space in our case. So let's say that this is the Jacobian between the Cartesian space and joint space. So it was what? It was x dot is equal to j q dot, right? So what are the components of the Jacobian? So let's see this case. So here there are how many joints? There are 4 joints. Okay. So if there are 4 joints, and there are how many variables with which respect to we are taking the Jacobian? There are 3 variables: px, py and pz. We are not talking about the roll pitch yaw. Roll pitch yaw of the end effector we are not talking about. If it was a 6 degree of freedom, then we would also have some information about roll pitch yaw. Okay, so we have px, py and pz. Okay, so we have that information. So what we will do with respect to px, with respect to px, partial differentiate with respect to q2. Py with we will partial differentiate with respect to px we will partial differentiate with respect to q3, and px will partial differentiate with respect to q4. And similarly, second row will be for py, q4, and third will be for pz. Okay, so this is like 3 cross 4 matrix. Okay, now in maths also you will find this when you are doing linearization and all. For that it is required, or in Taylor series or two-dimensional Taylor series, there also you will require this matrix. Okay, so uh, it is you can go and read about Jacobian, not just in terms of robotics, but in terms of, it's like very useful matrix in research. Okay, so now let's see how to compute this. Even though this is looking too much, it is very simple. So they have given us what is the value of px. So px is given as n1 c1 plus n2 c12. Okay, So what will be dou px dou q1? Who will tell?
It will be a constant value, sir, minus n c sine theta 1 minus a to n2
My
sine theta 2 minus 2
Okay, minus
plus
n1 sine theta s1. So this is cq
uh,
c1 means cq1. Okay, and
yes,
c12 means cq1 plus q2. So for those,
c
if someone has the
yes,
doubt, then I will just write. Okay, so this will be minus
yes,
cos ka derivative is sine. So it will be minus sine of 1
uh,
plus q1 plus q2.
right.
Okay, now let's find like that. If you continue finding, we will find some of the values and we will check. So dou px q dou with respect to q2 will be what? This will be 0 because there is no q2 in this. So partial derivative, if anyone has doubt on how to take partial derivative, please ask. Everyone is fine with partial derivative. Let's say if this is x square plus y square plus 2xy. Okay. How do we take the partial derivative with respect to y? It will be, this will become, so x square ka partial derivative with respect to y will be 0 because there is no y. This will be 2y and this will be 2x. Okay, fine. So
Yes, sir, that is it.
yeah. So okay. So for dou px by dou q2, you will get only n2 s12. Okay. Similarly, let me take a randomly something. Okay, let's compute this dou pz by dou q2. Okay. So let us see what is pz d1 minus d3 minus d4. So it is d1 minus d3 minus d4. So all the values don't have theta, so this will become 0. Okay, so that is how you solve this, and you will find that the answer is this particular thing given here. Okay, so this is the answer. Okay, so as we computed these terms. Okay, similarly you can compute other terms and you will get the answer. It's very simple. Okay, someone just joined. Okay, Aditya Sai has raised the hand. Please ask your question directly because I can't see your hands raised when I am in the presentation mode.
Okay, okay. Sir,
Yeah.
don't we have to expand the C Q1 plus Q2 and then differentiate?
Oh, okay. So yeah. So here, okay. Why when I write all the empty slides get this? I don't know. Okay. Here some spaces there. I will write. See CQ1. Okay. C12 is nothing but C cos of Q1 plus Q2. Okay. Now you don't have to expand this and differentiate. Right, you can directly differentiate cos of q1 plus q2 because see when you are differentiating doing partial differentiation with respect to q2. Okay, if I do partial differentiation with respect to q2, what is this is a constant.
Yes, sir.
Yeah, so it is like you are doing partial differentiation of 1 plus x, cos of 1 plus x. What is cos of 1 plus x ka differentiation with respect to x? It is what? Minus sine 1 plus x into differentiation of chain rule 1 plus x. So this is minus sine of 1 plus x into this will be 0, this will be differentiation of x is 1. So it will be minus sine of 1 plus x only. So you can directly do the differentiation. You don't have to
Okay, okay.
expand like
Okay, sir.
cos of 1 into sine of x like that. Those formula you don't have to apply. Okay.
Okay, sir. Thank you.
Yeah. So let's go on to the next question. Okay. So again, why this thing is coming up in this slide? I don't know. Okay, let me erase everything. draw eraser. Getting worse. Okay, give me a minute. Okay, let's ignore the written part here. We can, I think, deal with it anyhow. The question is very simple. So we have been given a matrix B. Okay, are you with me? Hello, can you hear me? Yeah,
Yes, sir, we can.
yeah. So we have been given a matrix B, and we have been asked to find the pseudo inverse of B. So why they are asking us to find pseudo inverse and not inverse? First of all, what is the meaning of inverse of a matrix? So when you say inverse of a matrix, it means any matrix that, let's say we want to find inverse of matrix A. It means that AX is equal to XA is equal to identity matrix. Okay, identity means the matrix which has all ones. Okay, so why can't we find directly the inverse of this matrix? Why we need pseudo inverse? Because this matrix is a rectangular matrix and not a square matrix. So when you don't have a square matrix, you cannot find the inverse. Okay, you can find inverse only of a square matrix, and not all square matrices you can find inverse, but if at all you can find an inverse, the matrix should be square. Okay, now why not all square matrices we can find inverse? Because there are some non-invertible matrices, and when is the matrix non-invertible? When some of the rows or columns are linearly dependent on each other, or you can say that let's say for example, if it is like 1 1 1 2 2 2 3 4 5, so as you can see, this particular row and this particular row are dependent on each other, not linearly independent, so the determinant of this matrix will become 0, right? So if the determinant of this matrix becomes 0, we cannot find the inverse of this matrix. So that is one reason when we cannot find the inverse of a matrix. So let's say like the as you might have learned, the formula for inverse is adjoint of A divided by determinant of A. But if the determinant is 0, then denominator is 0, and when denominator is 0, the number is not defined. Okay, or sorry, the equation or anything in mathematics is not defined when we get denominator 0. So we cannot find an inverse. But here the reason for not being able to find inverse is different. It is because the determinant itself is not defined for such thing. You might have never seen determinant of a rectangular matrix. So it is not possible to find inverse also. So how to find inverse of such matrix? So for that there is something called as Moore-Penrose inverse. So this particular mathematician has given this formula over here. So when m is less than n, okay, so when m is less than n, you apply the first formula over here, a transpose a transpose ka whole ka inverse. Okay, and when m is equal to n, it is just a inverse, and when m is greater than equal to n, then a transpose a inverse into a transpose. Okay, so here there is nothing to be done, just take a b is given. What will be b transpose? B transpose will be like, just make this vertical, right? So the first column will become first row, second column will become second row, third column will become third row. So this is B transpose. Okay, And now you know B transpose, you multiply them, you'll get a matrix, take inverse, then multiply by B transpose. So it's just you plug and play. Okay, that is just a formula. You know matrix multiplication. So in the interest of time, we will not do the matrix multiplication over here. But if you want, we can verify this answer in MATLAB. So we'll just go to the MATLAB. Just remember this formula. It will one question usually will come like this. So either m will be greater than or less than n. So when m is number of rows, n is number of columns. Okay. So it is accordingly we have to choose the right formula. Okay. So MATLAB is loading. Till then we can go to the next question. Is there any doubt in this question? We can go to the next question.
I'm sorry, sir. I just went to the washroom real quick. Could you just repeat the last part where you
Yeah,
derived
I
this
said
pseudo
that if m is
function?
less than n, the number of rows is
Yeah.
less than number of columns, then you apply
Okay.
the first formula. Okay, so you
Okay.
just take the transpose like this,
Hmm.
B into B transpose, inverse. So the B into B transpose will be a square matrix. So square
Yes.
matrix
Right.
inverse you know how to find, right?
Yeah.
Yeah, and you multiply by B transpose, then you will get this. When the number of rows is less than number of column. In this particular example, number of rows is number less than number of columns, so you apply the first one. If in the question it is given that your matrix is a like a vertical matrix where the number of rows is more than number of column, you apply the second formula, this formula. Okay, that's it.
Uh,
This-
okay.
yeah,
Okay, sir. Just one doubt I had. My
yeah,
apologies for interruption.
yeah.
When we're talking about inverse,
Huh.
so are we saying that we use that principle of finding out the cofactors and then adjoint of the matrix and then 1 divided by determinant? That is the
Yes, yes,
process.
yes. This formula that I have written here, A inverse equal to adjoint of A divided by determinant of A. So if it is a
Okay.
3 cross 3 matrix, then you
Hmm.
have to do that way. Okay, what you
Correct.
said.
Right.
If it is
Because
a
we need a square matrix.
yeah,
Yes.
you need
Correct.
a three square matrix. So A transpose A, this will become a square matrix. A transpose A, like that.
Yes.
Yeah, here you have to
Yes.
find the inverse. Okay. If it is a 2 cross 2 matrix, there is a shortcut. Okay, you can look up in the Wikipedia. You don't have to do the cofactor and all. Okay,
Hmm.
you interchange the non-diagonal terms and put a
Okay.
minus sign on that and divide by determinant. So that formula is there. Okay, so it is
Okay.
yeah.
Right.
So let's go to the next question. Okay, okay, this is not visible over here. So what I will do is I will yeah, I will do this like this. Okay, so at angle theta 2, the manipulator attains boundary singularity given the dexterity equation of the robotic manipulator as dex k1 k2 into h2. Okay, so they are talking about the same manipulator over here. Okay, so they are saying at theta 2. Okay, so again this figure also I should copy. So at angle theta 2, so theta 1, theta 2 over here. Oh no, so this is the joint. Okay, what is the question number? Okay, yeah, so this is theta. So it is little bit weird. Okay, so theta 1 is this angle, theta 2 is this angle. Okay, fine. So Z1 and Z2 are parallel to each other. Okay, and they are asking us that what is the uh, at what angle the manipulator attains boundary singularity. So first of all, what is the meaning of singularity? Okay, so singularity term appears in physics and mathematics or any technical discipline when things are unsolvable and when there are no solutions or solution become infinity or something like that, you say that there is singularity, like there is a singularity at the black hole or something like that. It just means that we don't know how to solve that. That is the way you interpret the word singularity usually. Okay, when they are saying boundary singularity, it means that uh, you you have reached, extended your arm completely. Okay, once you extend your arm completely, like all your like here, okay, your theta 1 is 0, theta 2 is 0, you extend it completely, you have touched the boundary. Okay, now you cannot move any further. Okay, so such configurations are called boundary singularity. Why they are called singularity is that at such configurations the Jacobian matrix that you have, that becomes non-invertible. Okay, sorry, not the Jacobian matrix, the J transpose J matrix. Okay, the J transpose J matrix. Why J transpose J we are considering? We are considering the J transpose J because uh, because our Jacobian can be a rectangular matrix. Okay, but J transpose J will always be a square matrix, and for analysis purpose we can consider the square matrix. Okay, because then we can take the the inverse of a square matrix exists, so we can find its eigenvalues, eigenvectors, and do some analysis with that. Okay, so such analysis is very much common in robotics course, robotics community, where we find the what is the what is the current configuration of the arm. Let's say, let me give you an example. Okay, it's kind of out of syllabus, but let me just give you an example. Okay, so this particular arm, I'll have a simple question to you. Okay, so let's say this is a arm, and it has to move in certain direction, let's say in this particular direction, and it can achieve certain velocity. Okay, now same two link manipulator in this particular configuration where the angles are, there is an obtuse angle in between. Okay, now in this particular direction it has to achieve a certain velocity. Okay, what do you think? Okay, this is theta 1 and this is theta 2. Okay, which particular velocity will be more for same angular velocities of the joint angles? So same joint, if the both motors rotate at the same rpm, okay, at what end tip you will get, more velocity, in this configuration or this configuration, configuration 1 or 2? Am I audible? Hello?
Yes, sir, you're audible.
Yeah, so
Most
this is the
likely the
question.
answer.
Yeah, what is the answer? You can just guess.
Most likely the second one, because there is more degrees of freedom as opposed to, I mean, the movement range of movement is more in the
No,
second
no, the
configuration.
length is same. L1, L2 only. L1, L2 only. This
Hmm.
is already extended, and this is not that much extended. Okay. So actually answer
Okay.
is that here you will get more velocity. Okay, for same
Right.
rotations, because here you have more flexibility to move around. Okay, you have lot of what you can say, the moment arm is also supports this direction. Okay, but here if you see, already you are extended so much, right? So
Hmm.
for example, if you want to slap someone, you would slap like this. Okay, but you cannot already
Right.
extend a hand, and then you don't have that much freedom to slap. Okay, so that kind of,
Correct.
so what should be the configuration to achieve a certain force or a velocity? Okay, that data is embedded inside the Jacobian matrix. Okay, so I am not going into
Okay.
details. So but if you see Jacobian is relating what? Jacobian is relating the Cartesian space of the end effector velocity to the joint velocity. Okay, so the relation is completely inside the Jacobian. Okay, so what and Jacobian is a function of q values, right? The angles.
Correct.
Okay, so these angles will tell you, okay, whether the Jacobian has the ability to produce forces or velocities and in what direction and how much. Okay, so that is why what we do is we you can mute your this thing mic, whoever is on.
Yeah. Sorry.
Yeah, yeah. So what happens is this Jacobian, you usually this is the procedure to find out these things. You find J transpose J. Okay, after that you do the take the SVD of it. Okay, and then you get three matrices U, sigma, and V. Okay, so this is all out of syllabus, but just you can just pay attention. It's okay if you don't understand it completely. And from U, sigma, and V, V has the eigenvectors. Okay, and sigma has the eigenvalues. Okay, and from eigenvectors you can find the directions. Okay, in the Cartesian space, let's say this is the manipulator. Okay, this is one joint, this is another. So these two directions you will some, let's say you find, you get from the eigenvectors, though these two vectors are there, and you will understand that in one direction it can apply high force, in another direction it can apply high velocity or something like that. In case of Jacobian, you will get a manipulability ellipsoid, and you can draw the ellipsoid using these two directions, and the length of this vector is determined by the diagonal entries of this matrix, which is a diagonal matrix. Okay, so when you do the SVD, you will get two orthogonal matrices and one diagonal matrix. Okay, so this is the theory behind the Jacobian. So it is a very interesting and deep theory that you can look up in any robotics book. Okay, but for our purpose, we just want to find out that where this Jacobian transport Jacobian is going to become non-invertible, or where we cannot find any inverse of this. So when does the inverse it becomes non-invertible? When the determinant of Jacobian becomes zero, right? So if you find the determinant of this Jacobian that we found in the last question, okay, you will get this something like this, some constant into sine theta. So this determinant it should become 0. So h2 should become 0. When is sine theta 2 will become 0? When theta 2 is equal to 0 degree and phi. Okay.
Correct.
So yeah, so this is the answer. Okay, so what you basically the procedure is, okay, I have given a lot of theory over here just for motivation purpose, but the answer is very simple. Whatever Jacobian matrix you have, you take the determinant of it, and then you equate the term which contains your angle to 0. Okay, oh sorry, you equate the determinant to 0, and then you will find the condition on the angle. Okay, so here they by themselves they gave that this is the determinant. So they said dexterity equation. So this is the dexterity equation. Determinant of J transpose J equal to 0 is the dexterity equation. Okay, so that is, and that is K1 K2 H2 equal to 0. Now K1 K2 H2 equal to 0 means H2 equal to 0, S2 equal to 0 means theta 2 is equal to 0 or pi. Okay, so if you have any doubts you can ask. Only this much you have to remember. The other things SVD and all you can just go and look up. Okay.
Right. So in the lectures also for the singularity part, I was just going through the transcript.
Hmm.
They were explaining that how singularity is an explanation of if the degrees of freedom on a number of joints is less than equal to 6, then the way of calculating singularity is determinant of Jacobian transpose times Jacobian.
Yes, yes, that's what we wrote here. Where we wrote?
Okay.
Huh. Here we wrote.
Yeah, this one. Yeah.
Yeah. Okay. So let's go on to the next question. Okay, so this is the DH parameter question. This time we have already seen this a lot. Okay, so how to solve this? We have been given the DH parameters of the spherical manipulator, and once we know the DH parameters, what we do? We, for each of this row, you will find the homogeneous matrix, right? How do we find the
Yeah,
homogeneous matrix?
I think
How?
there is a concept of arm matrix where we have to substitute the values of theta.
Yeah, yeah. So this is the homogeneous matrix directly we can get from the DH parameter. Like if you have attended the previous this thing, so you might have seen that how we do deal with this is that you can directly, this particular row is there, so you substitute theta 1, alpha 1 and all, d1 a1 you substitute over here and you get the matrix h1. Similarly you get h2 and h3. Okay, so you will get three such matrices you will get. Okay, then you just multiply h1 into h2 into h3 and you will get the answer. Fine, this is the procedure.
Yes, yes, clear.
Okay, so it is a very cumbersome calculation. Okay, you can use MATLAB for this, for if you can use a symbolic MATLAB or you can do it by hand. Okay, so basically in such cases, I what I would advise is, if you get such questions in exam, okay, you can do some smart calculation, that instead of doing the 4 by 4 multiplication, right, just do 3 cross 3 multiplication. That is also fine. Okay, because you just have to check the rotation matrices or something, because these matrices are not affected by the the fourth row fourth column when you're computing. So you can be a smart, or you can just directly go for the complete multiplication according to how much time you have. Okay, so this is little bit lengthy question but very simple. Just find h1 h2 h3 according to the formula and just multiply. Okay, so let's go to the next question. Okay, so this is from the previous, we have solved this question also. Okay. This is a very simple question, but okay, it is we can solve this. So we have given the position vector with respect to the base as this particular vector, and we have to find the value of d3. Okay, how are we going to find this? So we know the answer to the previous question. We need to know the answer to the previous question because it is based on the previous question. The answer to the previous question was this. Okay, when you do the matrix multiplication, you will get this. So what you do? So this is the px, py, pz. You write here d3 c1 h2 is equal to minus root 2 by 8. Then d3 s1 h2 is equal to root 2 by 8, and 8 minus d3 c2 is equal to minus root 2 by, sorry, equal to 8 minus root 3 by 4. Okay, and then we have
So
to
I think
solve
it's
this
just
equation.
substitution.
Yeah,
I
you
think
have
it's
to
just substitution.
substitution. What substitute?
I mean, the three values that you have, minus root 2 8 and 2 root 2 8 and 8 minus root 3,
Yeah,
you
yeah.
just have to.
You substitute in terms of here, but now you have to
Right.
solve this equation, na? How you will
Yes,
get the
yes.
value of d3? You don't know the value of theta 2.
No.
C2 you don't know. So you cannot directly find. To solve, what you will do, you use the trigonometric identity. So here you can see that S1 and C1 is there. So you square and add the equation 1 and 2, you square and add. What will happen then? You will get D3 square C1 square S2 square C1 square S2 square plus S1 square S2 square is equal to, this will be root 2 ka square will be 2, right? 2 by 64 plus 2 by 64, 4 by 64. Okay, that is nothing but 1 by 16. Okay, so S2 square
Yes.
you can take common, and what will happen? Inside will be C1 square plus S1 square and is equal to 1 by 16. C1 square plus S1 square is 1. Cos square plus sin square is 1. Okay, that trigonometric identity you have to use. And then you take square root on both sides. You will get D3S2 is equal to plus or minus 1 by 4. Okay, that is nothing but plus or minus 0.25. Okay, and you have one more equation, that is D8 minus D3 C2 is equal to 8 minus root 3 by 4. What you do is you put the 8 on other side. So D3 C2 is equal to 8 minus root 3 by 4. Okay, so 8 minus 8 minus root 3 by 4, you will get something like this. Then again you square and add these two equations. Okay, so you will get D3 square. So I'm skipping some steps here because S2 square plus C2 square is equal to 1. Okay, and you will get this entire square. So 8 minus root 3 by 4 the whole square plus 0.25 square. Okay, and when you do this you will get answer as D3 is equal to plus or minus 6.43. Okay, so this is how you might have to play with some trigonometric identity, but they have not considered the negative value of D3. Okay, they only consider the positive value of D3, but as we know,
Yeah.
depending on how we choose the axis, okay, you can get plus or minus D3. Okay, so it's okay. So let's go on to the next question. Not many questions are left. Okay, so here is one question.
So just
Yeah.
one thing, I was actually solved this using the subject of formula approach. So that's why I said substitution.
Okay, you solved it on another way. Good, good, fine. Yeah. So there can be multiple methods also. It's
Right.
okay. Okay. So consider a roll pitch roll wrist given below. So okay. So this is the roll pitch roll wrist. So this particular angle is they are considered as roll. Then there is this pitch angle axis, and then there is this roll axis. Okay. So when we say wrist, it is the something that is near the end effector, right? It is the last 3 degrees of freedom in a 6 degree of freedom arm, right? So which of the statements are false? So they have asked that the wrist has a singularity when theta 1 is equal to 0. The dexterity is 0 when theta 2 is equal to 180 degrees. Okay, we know what is dexterity. Dexterity is nothing but J transpose J ka determinant. Okay, and that question was for the spherical wrist only. So we already know that from the previous answer that when theta 2 is 0 or 180 degree, the dexterity is 0. Right? Do you recall that?
Yes, sir.
Yeah. But yeah, but this is roll pitch roll wrist, not a spherical wrist. So I don't think we can directly apply that over here. Okay, but the basic is that you have to find the J transpose J ka determinant for this to know whether that dexterity is 0 or not when theta equal to 180 degree. Okay, so that is how you find whether that particular option is correct or not. So we will not go into that, but that is how, that is the hint that is given. And wrist, the wrist has a singularity when theta 1 equal to 90 degree or not. The wrist has a singularity when theta 2 equal to 0 or not, or the wrist does not possess any singularity. So that is the statement that is given. Okay. So how to approach this question? So one thing is by inspection you can approach. Okay. So the wrist has a singularity when theta 1 equal to 0. So one intuition of singularity that can be seen is when you rotate, just a minute. अरे आवाज बिवाज करू नका ना आणि हा वळवळ पण करू नका. Yeah, sorry for the disturbance. So the thing is, your one angle is rotating. Let's say this rotates by 30 degree anti-clockwise. Okay, and this particular thing rotates by minus 30 degree clockwise. What will happen to the end effector? End effector will not move. Are you understanding? Can you imagine this?
Yes, it
Even
actually
though,
goes into a deadlock.
yeah, so even though the joint angles are moving, the end effector, there is no effect on the end effector, right? So that means that Jacobian matrix, which is responsible for this end effector motion to get translated from the joint angle velocities, that Jacobian matrix is not able to translate that. Okay, so your q dot is changing, but your x dot is not changing. Okay, so that can happen in this particular configuration. Okay, when these two axes are parallel, the both roll axes are parallel, and when both the roll axes are parallel, when your pitch angle, your angle theta 2 angle is 0, right? So or the theta 2 angle is 180 degree also, it is possible. So if you see here theta 2 angle 180 degree or theta 2 angle 0, according to me this should be the answer. Okay, but here I think there is some problem. uh,
No, actually, sir, it's correct because they're asking which are false. So the
okay,
ones you
okay,
marked, it's
okay,
actually
okay,
true.
okay, 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 yeah, 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 thanks for that. So they are, yeah, so this is true, right? So theta 2, so our logic is right,
Yes.
theta 2 equal to 0 and theta 2 equal to 180 degree, we will get a singularity. Okay, so this is true. So whatever is remaining should be false then. Okay, so this doesn't have any logic. Okay, theta 1 equal to 0 or not, for any value of theta 1 we can get a singularity depending on the value of theta 2. So this is wrong, then this is wrong. Okay, so theta 1 actually, see, usually na, you can, this is the trick that you can remember for wrists. Okay, or for even chord rotors. Okay, when you write the Euler angle or the rotation matrix and all, you use the roll pitch yaw configuration. So the middle angle, okay, in this case is theta 1, theta 2, theta 3. Always the middle angle will be the cause for the singularity, never the first and the last angles. Okay, because of the middle angle, your first z axis and last z axis gets aligned, and then the singularity occurs. So always remember the middle angle is the culprit. So these people, when they are talking about theta 3 and theta 1, they are not going to affect in any way. So theta 1 and theta 3 cannot affect your singularity thing. So this is false, and the which does not possess any singularity is like, contradicting all the statements above. So it has to be wrong. Okay, so this is the answer. So only theta 2, and yeah, so this we are able to find without finding the dexterity equation. Okay, without doing this we were able to conclude, because we just did the observation that when theta 2 is 0 or 180 degree, this z axis and this z axis will get aligned, right? And when they are getting aligned, if this rotates by, let's say, 30 degree here clockwise, and this rotates opposite direction anti-clockwise, then the end effector is not moving at all. Okay, so this is a singular configuration. Okay, so that is how we were able to conclude. Okay, so now let's go to the next question if anything is remaining. Okay, let me just check whether the recording is okay. Recording is proper. So do we have any question left? Okay, so we have the last question. Yeah, so this is the last question. So I already have discussed about this little bit earlier. If someone has joined late, then they cannot listen. Yeah, so I had discussed that Jacobian not only relates. Okay, so this is wrong. Jacobian not only relates the end effector velocities with the joint angle. So what do you mean by end effector velocity? Px dot py dot pz dot is equal to Jacobian into your theta 1 dot, theta 2 dot, and whatever. How many angles are there? Theta n dot. Okay, so this is not only this. So the dimension of Jacobian in this case will be 3 cross n. Suppose I write this as px dot py dot pz dot roll dot pitch dot and yaw dot of the end effector. So if it is a like uh, all degree of freedom we want to write Jacobian, so this will be j into your depending on how many angles it has. Sorry, joints here. Let's say it has 10 joints. Okay, so this will be 6 cross 10. So in general the Jacobian is 6 cross the number of joints. Okay, because 6 will always be there, right? The 3 positions and 3 orientations of the end effector will always be there, but usually we are mostly interested in the velocity of the end effector, so we only consider the first 3 rows. So like px dot py dot p dot pz dot. So in most of the examples you see Jacobian has 3 cross the number of links. So like we had in the earlier case, in this case we had 4 cross so no, this is not a Jacobian. Yeah, so in the previous question we had 3 cross 4 Jacobian, right? Because there were 4 links. Okay, so let's find out what force would the joints have to produce if the static load of this with 0 Newton meter moment is acting on the tool. Okay, Fk is the force applied by the joint K and Mk is the torque produced by the joint K. Okay, so how do we find that? So for force and torque, I have already given the formula. So what is that? F is equal to, sorry, tau is equal to J transpose F. This is the formula. What is the Jacobian of this matrix? That was that we found, right? We did by partial derivative. We found that Jacobian. Let's go and pick that up where it is. Where did it go? Here. Yeah, this is the Jacobian. So this was the Jacobian, and this is our question over here. Okay, so we have to find, we just substitute the force over here, 0.4, 0.6, 0.8, right, is equal to this Jacobian.
It will mostly be, I think, a 0 and 1 matrix because it will all have zeros and ones filled.
One. So it was, sorry, it is J tau is equal to J transpose F. Okay. So here is the Jacobian, and here is the Jacobian transpose, and here we should get the torques. Okay. So what force would the joints have to produce if a static load of this is given with a 0 Newton meter moment is acting on the tool? Fk is the force applied by the joint K, and Mk is the torque produced by joint K. Okay. But they haven't given us any configuration. So they haven't given us the value of theta 1, theta 2. So without theta 1, theta 2, how we can find? So they should provide us theta 1, theta 2, no? Okay, let me just check if I am doing any, missing any piece of information. Okay, they have given us the, okay, the information over here. So let me pick that up. Yeah. Yes. So this is the, these are the values. So once you have the value, you can just substitute. Okay, so they have given the values d1 equal to 10 and d2 equal to 15, d3 equal to 10. Okay, theta 4 equal to 60 degree. Okay, so as we have seen how to find the Jacobian uh, of any particular uh, configuration. So how do we find that? So we did the h1 into h2 into h3, right? We did this. After,
Yes, sir.
yeah, after that what we did the partial of h with respect to q. That was our Jacobian. This is the second step. This is first step. This is the second step. Okay, once we get the Jacobian, what we will do? We will substitute these values in the Jacobian, right? We will put these values inside the Jacobian and we will get J transpose. After that we will get J transpose. Once we get J transpose, okay, then what we have to do is we have to just as they have asked for the force, okay, we will get the force depending on. So still I think there is some information missing in this question, because Fk is the force applied by the joint K and Mk is the torque produced by joint K. So where is the tau K? Mk values they haven't given us. Right, they haven't
No,
given us the
actually,
value of Mk.
sir, actually, there's one thing in the assignments that we have.
Huh.
There is a DH table that is given, and
Okay.
based on that DH table, this question followed.
Yeah,
That based on the
based
DH
on this
table and
DS
given the
table, we
K.
found the H. We found the H based on the DS
Yes,
table.
yes, yes,
Then
and then
after
K was
H, we
also given.
found the J also we found. Right.
Yeah, correct.
After J, we got the J also. We have, see, in this equation we have J transpose F is equal to tau. Okay. Now they have asked us to find F. Okay. So what we do, we take the Jacobian transpose inverse. We will do this Jacobian transpose inverse. Okay. We multiply on both side. Okay. So what we will get, F is equal to, you do the Jacobian transpose inverse. If it is a rectangular, you do the pseudo inverse that we have found, and you multiply by tau. But the value of tau should be given, na? The value of tau is not given.
Um, may I share my screen and show you something, sir? Would that
Yes,
clarify?
yes. Yes, yeah, you share the screen. Right. Yeah, yeah, you share. I will just turn off the this thing.
Sure.
Wait. Yeah.
I hope my screen is visible.
Yes, yeah, the screen is visible.
So this is where they compute the Jacobian based on the DH parameter where my cursor is hovering.
Yeah, yeah, this is fine. This we have seen already, but they haven't given us the value of the torques.
I'll come to that, sir.
Hmm.
Just let me skip it a bit forward.
Yeah, yeah.
So this three equations that we get on
Okay.
the for the p, x, y, and z,
Yeah, yeah.
and now
Then
what the assumption was that
PXPY you
consider
take
these
the
three.
the partial derivative, you will get the Jacobian. Okay, you got the yeah.
Yes,
So this we did in the previous question, but after that they are not giving us the torque values. Yeah.
yeah. So torque is not actually calculated over here. We simply calculate the Jacobian. Once the Jacobian is calculated, this formula is applied.
Yeah,
Torque
but to
is
apply that
Jacobian transport.
you should have torque, na? Tau left hand side. Where is that?
This is how they had done it.
Yeah,
The
but to
tau they have
yeah.
assumed as 0,
Okay, they are
and
assumed
inside
as
this is the
no, no.
yes.
Even in this, there is problem. So if you have fx, fy, fz, you have to find the value, right?
So here they have taken as the scalar values on this question itself.
No,
Is the
no.
same
But
question. What for?
yeah, so you take the scalar values on point 0.3, point 0.5, point 0.8,
Point two. Yeah. Which
8.
is in your question is for point 0.4, point 0.5,
Okay,
and
okay.
point 0.8, I think.
Acha,
Yeah.
acha. So, okay, so they took that as what?
I'll just skip this
Okay,
once
okay,
again.
okay, okay, fine, fine. No, no, I understand they have done this, but where are the joint talks?
There is no specific value for joint torque set. What the explanation was given to us is actually a recording of the last class. The torque value is kept as unknown, and the value of this multiplication is coming around to be zero point 0.8, zero point 0.3, or
No,
one of
for
the choices.
this equation that is written over here, to my under best knowledge, this equation is wrong actually, because this J transpose into F is there, Fx, Fy, Fz is there. Okay, okay, so that is correct. Right hand side is completely correct. The left hand side, the four that this is given, those are joint talks only. Okay, this is tau 1, tau 2, tau 3, tau 4. Now, but what they are finding is they are treating this as a force, joint force. Okay, so
Yes.
this I am not understand how it can be a joint force, because is this particular prismatic joint or something like that?
Yes, that is what was told. It was a three prismatic and one rotating.
Okay, okay, okay. So that is why, okay, that is the confusion. Okay, so the if it is a prismatic joint, then it is fine, because for prismatic joint it will be a force, and for a regular joint
Correct.
it will be torque. Okay.
Torque. Right.
Yeah, yeah. So then this is this procedure you can follow. Okay, this is correct. Okay. In our question, like if you see, uh,
Right.
okay, in our
I have
question,
stopped my screen share.
yeah, yeah,
Yeah.
you can stop your screen share. Okay, so my screen is visible, na now.
It hasn't been shared yet, sir.
Okay, resume presentation. Okay, I'm not able. Okay, resume presenting. Yeah.
Now it is shown.
Yes, yes. So in our question, yeah, it was mentioned as the Cartesian manipulator that I missed. Okay, so it is mentioned as the Cartesian manipulator. So in that case, it is right. It
Yeah.
will be the same equation. So it will not be J transpose is equal to tau. It will be equal to F only. Okay.
Hmm.
So you can solve it in the similar fashion. So we have finished our questions for today. If there is any other doubt, then you can ask.
No,
Uh,
sir.
so,
Would request
so
you to upload the recording right away because in the previous one it was delayed till the last time. So
acha, acha,
we can
yeah,
just have a look.
yeah, I will upload the recording today itself. Okay. So any other doubt in any other questions or something like that, you can ask.
None from my side.
Okay. So Anirudh, do you have any doubt or any question you want me to repeat?
No, sir. My name is Anirudh. I just said
Oh,
I
sorry.
have no
Yeah,
doubts.
yeah.
I think Aditya might have.
Aditya, you have anything?
No,
So,
sir, no
so
doubts.
last question, because there was so much confusion, I will go through the steps. So you have been given the DS table. Okay, from each row you find H1, H2 and H3, the homogeneous matrix. You multiply those matrices, okay, in this order. Once you multiply, you will get a 4 cross 4 matrix. Okay, then from this particular column, you get the first three elements. Okay, these three elements you do the partial derivatives. Okay, dq1, dq2, like that. You do the partial derivatives and you fill in the Jacobian matrix. Okay, so you will get like px1, so dou px divided by dou q1, dou px divided by dou q2, like that you fill. Okay, dou pz equal to divided by dou q1, like that you fill. You will get a 3 cross something matrix you will get. Okay, if there are four variables, you will get 4 cross, means depending on how much joint how much end effector variables you are considering and how many joint angles you have, you will get 3 cross n matrix or 4 cross n matrix or 6 cross n matrix. So you once you get that, okay, what you do is you find the J transpose, okay, and you multiply it by F. Okay, then you will get the joint variables here you will get. Okay, so in this case it was a prismatic this thing, so whatever first three values will be there, that will be the joint forces. Okay, but if it was a rotary joints or revolute joints, then you would have got joint torques over here. Okay, but very important that this side thing is the end effector forces, the forces given in the question, like the point 0.3 I hat or point 0.4 J hat or something like that. And the left side thing is the joint forces or the joint angles, joint torques. Okay, so this was the our last question. So if there are no further doubts, yeah, anything someone is saying? Hello? Yeah, if there are no further doubts, we can end the session over here. Yeah.
Thank you, sir.
Okay, okay. Okay, thank you.
Thank you, sir.
Bye. Yeah.